little bit of backstory about Polars before I dive too deep, dive a bit deeper. So Polars itself, the open source project, is about 4 years old now. It was written originally by Richie, who is also in the room. Here you can see him with the same t-shirt. And he was always doodling around with his hobby projects, and then eventually he landed on Polars as kind of a main thing. And it got incubated here actually at Xomnia a little bit, because Xomnia sponsored quite a bit of his time to get out of the weekends and evening hours and to get him into the daytime. And well, the more time he spent, the more feature complete Polars became. And yeah, it's been quite a ride since. And I'll briefly go through all the features Polars has to offer. About 1.5 years ago, he approached me and he asked, Giel, I'm getting a lot of attention now, and I want to start a company. Would you want to join me? And I figured, yeah, I have a kid coming up. I'm already going to be sleep deprived. Why not make that even worse and basically help this guy start a company? So yeah, it was a rough year last year, but I'm still there, and well, it's a really nice experience, I can tell you that. I'm super proud of where we are, and I'm super proud of what's coming. I'm really excited for the ride. So for those unfamiliar with Polars, well, it's a DataFrame library. It's different from a database in the fact that we don't actually have a storage backend, so we don't store the data ourselves, but you can read from like all the familiar ones like the S3s, the cloud buckets, databases, just your regular file system. Anything goes nowadays. And we're written in Rust, so our core is in Rust, but most of our user base, like 95%, comes from Python, just because it's so much easier, so much more flexible to use. We also have community front end in R and Node.js, but they're a little bit less known. Yeah, so you might be thinking, why do we need another DataFrame? I mean, there are lots out there, right? I mean, we have Pandas, we have PySpark, we have a bunch of Pandas clones, or at least, well, versions of Pandas. And I think what we see happening a lot is the single machine is getting a lot more powerful. We get a lot more cores, we get a lot more threads, we get a lot more memory. I mean, the things we're able to process nowadays with a single machine is quite a lot. And a lot of workloads actually fit on a single machine nowadays. And that's where Polars really shines. I mean, we're a single node DataFrame, and we're able to process a lot of memory, a lot of data really fast, just because we keep it all on a single machine. And in the past, things like Pandas were not really designed with performance in mind, just because as soon as you wanted performance, you would go to a cluster and then you go distributed, and then you get all the problems that come with distributed, but all the benefits as well of being able to handle a large amount of data. But nowadays, with the single machine, you can actually do a lot. Polars and numbers were, well, we actually already up there. We reached 25,000 GitHub stars last week, or we're moving really, really fast. We're 4 million downloads. Our team is based in Amsterdam. We're with 7. And we have 4 other developers in different companies who are very active contributors who are also members of our core team. And nowadays, we're based on Apache Arrow, our memory format, which gives us a lot of freedom in the ecosystem to move around and to share our data with others. But we see first order support nowadays in the bigger libraries like scikit-learn or Hugging Face, who are also very active in the Polar space. So for today, what I wanted to do was, like, what I always like as a person, I like to know what's underneath. So as a user, you mostly just touch on the top side. I mean, I think this picture doesn't even do it justice because the top side is quite big, but I couldn't find the tip of the iceberg that was smaller. But what I want to do today is kind of go below the surface a little bit, because when you interact with the DataFrame API, there's a lot of stuff happening underneath. And I want to kind of take you through the top, but also like move a little bit down so you know what's happening. I mean, it's not necessarily that you need to know what's happening, because we try to hide it from you as well. But sometimes like knowing what's underneath makes you able to reason about why certain things might be slow or why certain things might be fast. So it kind of helps you, although we try to abstract it away as much as possible. There are going to be cases when you would want to know. So our API, it's a sort of it's a blessing and a curse at the same time, having the ability to design your own API. If you're not SQL-based, you have a lot of freedom to do things, and you get a lot of freedom to experiment and to go around. But yeah, if you're new, that also means like people have to learn your API. And that's kind of a steep learning curve, because people are already used to SQL, so it's a bit of an investment. But as we get bigger, we see a lot of people make the jump, and people enjoy our API a lot. And it's very functional, so we get a lot of inspiration from the functional space. And we try to basically nudge you towards writing fast code. I mean, it sounds like quite obvious, but you'll see an example in a bit where we want to make it like really, really tedious for you to write slow code. So, I mean, there shouldn't be a statement that you think is going to be fast and that ends up being really slow. Like, you would want to have sort of a sense, like a tingling, like when I'm writing this, it doesn't really feel right. There should be another way to do it, and there should be just a fast way to do it. And that's sort of what we think about when designing our own API. Our API is very much based around the concept of expressions. You can pipe expressions to create complex expressions. They're sort of like building blocks. And with that, you can create very powerful statements that are not super verbose, but they remain rather short. The idea is that you have a data frame, you have some inputs, and we call them series here. Our expressions also work on groups. So if you have like a group by context, you can also put them there, and they output a new column. So that's sort of the algebraic form. And although the building blocks themselves are quite simple, by combining them, you can get quite powerful expressions. At least that's our opinion. In reality, what's going to happen when you design an API is that you have certain vision of that's what we want to have happen. And then what ends up happening is, people say, fuck it, I'm just going to go straight. I mean, even though in this example, straight is shorter and possibly better for the user, in reality, what ends up happening is straight means that's the way I know, that's the way I'm going to do it, but that's probably going to end up in slower code. So one big example of this is the sort of dreaded, at least on our side, the dreaded apply statement. As a user, you know Python, so you know how to do things in Python. So the easiest way to go about it is to say, I'm just going to write a custom function, a UDF. I'm just going to say, I know how to do this. In this case, we have a data frame with some raw JSON, and in the apply, you put in a lambda, or in this case, it's a lambda under the hood, but it's a JSON load, so the JSON library of Python, and you're going to load the JSON. But you can define any custom function there, and for the user, this is really nice, right? I mean, you get to do your own stuff, you get to do what you're used to, writing native Python. But for us, as a query optimization perspective and query engine perspective, it's really annoying because this is this opaque function. We don't know how to optimize. We need to get the data across. This is going to be painfully slow. So what we end up doing is to avoid this disaster, we end up analyzing the bytecode of the UDF and say, okay, would there be a way to not do this, but to use our own API instead? I mean, it might be a little bit hard to read, but it says Polar's inefficiency warning. that should already be enough by itself. But then it also gives you kind of like a hint, like saying, oh, replace your expression with this one instead that uses our native API. And that way, our query optimizations, techniques, everything, our parallelization can just work and go ahead. So we spend an awful lot of time to make sure you learn it, but we promise that once you learn it, it will be fast and it will be great. So for today, I kind of want to take you through a kind of simplish query, just to get through the motions of what is happening under the hood and like how do we get from a query all the way to a result. It's a quite familiar data set, I would say, the New York taxi data set, so their trip data, where you have the amount, a zone in which things are happening, you have a pickup time, you have a drop-off time, pickup location, things like these. Anyone who've spent quite some time on the open data sets probably has seen this before. And what we want to calculate is the average cost per minute per zone. So how much does a minute cost in each zone? In polars, that would kind of look like this. Where we scan a parquet file, we join it with the CSV file that contains some zone data, and then we filter, we group by, in the aggregation itself, that's what the AGG stands for. We can also put in an expression, and the expression itself divides the total amount by the amount of minutes that is out there. So far, I would say this is at least quite readable, and well, I mean, it's a simple query, but by itself, it's also not super verbose. By defining your query, you're not actually executing it. You're sort of only defining what you want to happen. So it's lazily executed. We're not actually executing the query at the moment. And the reason for this, I'll explain in a bit. Once you write the query, we actually parse it into a logical plan. So the logical plan kind of describes your intent, but only then from a sort of internal perspective. Like, this looks natural from the outside, and this is how we see it from the inside. A logical plan usually reads from the bottom to the top. So in the bottom, you have the data sources, you have the parquet scan, CSV scan, the join, the filter, and then the aggregation. This is, yeah, I mean, also quite readable, I would say, but it's not the most optimal way to execute it. I mean, as a human, this is readable, but for a computer, there are better ways to execute it. And that's what our sort of a query optimizer is for. We want to take the responsibility of writing an optimal query from you. And that might seem a little bit weird, but on the one hand, it's you want to write an optimal query. On the other hand, you shouldn't have to worry about certain things. And that's what the query optimizer does. Like, you shouldn't have to worry about where the filter is. You shouldn't have to worry about if you want to read in all the columns from a data set or just a few. Like, we're also columnar based. You shouldn't have to worry about having duplicate calculations. The query optimizer takes that away from you. So there are quite a few of these optimizations. Like, we want to check the schema if the types are correct. We want to only select certain columns. We want to apply filters as early as possible. If there are any constants that we can get rid of, we prefer to do that as early as possible. I mean, this one is quite simple, but sometimes we see query plans like take up 4 or 5 monitors, and then especially with self-joins, you end up reading the same data set twice. So with scan sharing, you can sort of cache the data set in memory, so you don't really need to read it twice. Subplan elimination, if you have plans in the tree that overlap, you only want to do those once. And there are a lot more. I mean, these are just the tip of the iceberg. There's a lot more happening that sort of takes responsibility from you. You want to write your query the way you want to write it, with sort of readability in mind. And then from like a query engine perspective, we want to to tweak the plan a bit. So we end up traversing this tree quite a number of times just to get it right. This is an NP hard problem so it's getting to the optimal solution is not easy, but it's a bit of the magic of writing your own query engine. So if we look at one of those techniques, like predicate pushdown, if you're unfamiliar with predicate pushdown, that is, we want to apply a filter as early as possible. If we look at the earlier logical plan, we end up reading, once we actually materialize, we end up reading all the data. We join the data and then we throw away quite a bit of data. Like we throw away everything with the amount is more than 25. So it's a bit wasteful, right? I mean, if the filter was before the join, it would be nicer because then we didn't need to join on the data that was actually going to be thrown away later. That very basic concept is what predicate pushdown is all about, that you want to filter as close to the data as possible. So you want to filter when you're reading the file, you actually want to throw away the data already, or even not go over the network when you're reading from S3, for instance. A common file format in this is Parquet. In Parquet, the structure sort of looks like this. I mean, it's very high level, but Parquet file is a header and the data itself, which is split up in groups of rows. So if you have like a file of 1 billion rows, and then you split them up by 1 million of rows, you can get these row groups. And then for each of these row groups, you store some metadata in the end, like column amount. The minimum value in this row group is 5, and the maximum value is 10. And the beauty of predicate pushdown is then instead of having to read the data, you can immediately go to the metadata and try to find out, does it even make sense to go through this row group? Like if I already know the maximum is 10, I can just skip that entire memory region. So these optimizations are very, very powerful. And by being lazy and by waiting until your query actually materializes, we can do these types of like projection pushdown, predicate pushdown that are really common in the database world. We can also apply them in the DataFrame world. So when we're done and we've traversed this plan quite a bit, we have an optimized logical plan. You can ignore the fast project. It's going away, I've heard. I was also wondering what it actually is. But so the thing that should stand out is the filter is now gone. It's moved from the part where fast project actually was, and it's moved into the Parquet scan. So that's what the predicate pushdown is. When we read the Parquet, we actually want the predicate, the filter itself, we want to have that in our I/O readers. Same thing that happened with projection pushdown is instead of, that's the pi symbol all the way below, instead of reading 19 columns, we end up only reading 4. Those are the 4 you actually need, so we can remove the need to read all the data. And I would say that's sort of the beauty of being lazy. In the human world, that's being lazy is considered not as a compliment, and in the database world, being lazy is usually really good, because it means you're going to do the minimum amount of work that needs to be done to get to a result. When we execute this in Polars, executing the query actually means you write collect. That means like I'm done, I'm going to execute it. We can remove all the optimizations, and then we'll see that the wall time is around ½ second. And then when we do with optimizations, we can see that's around 100 milliseconds. So it's a 4x improvement just by applying all these optimizations. So having a query engine underneath your DataFrame library is really strong, because it allows you to reason about the intent, and it allows you to perform these optimizations. A bit about execution. I mean, I'm not going to go too much in detail here. We are completely written in Rust. You see some more Python libraries go there. I've seen Pydantic is also now moving its core to Rust. There's an excellent library Pyo3, which sort of combines the two worlds. And as like a library maker, it's really nice because you get like the low-level benefits of Rust and being able to sort of control your memory really well, have a lot of control over your cache, but expose yourself in the Python world where users can have all the flexibility and all the nice things that Python has. Yeah, just some things that we try to make Polars as efficient as possible is SIMD, single instruction, multiple data. That is to have, instead of going one by one and have like 1 + 1 be a statement, in most processors nowadays, they allow you to process a lot more data at once just by having some registers in your CPU. And I think the one that is going to provide the most benefits, that's the parallelization. That is what I started with. I mean, nowadays computers, they have 4 cores or 8 cores, or I don't know how many cores are even in a single phone. It's already quite a bit. So yeah, you have a lot of resources available to you, even on a single machine. So why not use those resources? I mean, it would be a waste if you waste some resources, right? So there's quite a funny clip of a data engineer was live streaming his work, and he ends up running a Polars query. But Polars is quite hungry. It takes what it gets. So if you run a query, it tries to get as much resources on the machine as possible because that's generally what you're looking for. So when he runs the query, his live stream cuts out just because there's no more CPU or memory available to him, and then everything else on the machine crashes. Of course, there's configurations to get around this, and we do allow you to sort of say, oh, this is the maximum threads you want to work on. But in general, I mean, use what you get, right? That's sort of the philosophy here. But to get everything to maximize its resources, Polars uses an algorithm called work stealing. It'd be great if someone stole my work, but in general, it means that when you do an operation on a column, you do this on a single thread, you end up wasting all the other threads because they're doing nothing. So one strategy you could use is split up the column, split it in our example, in 8 chunks, and then have each thread do 1/8 of the column. But we don't really know if everyone's going to finish at the same time. So it might be that your operation is really slow for one chunk and then it's really fast for another. So if we do that strategy, it ends up like one thread being done early and waiting on the final thread to finish, because we need all the threads in this case to finish. So a better strategy would be to split it up even more into tiny chunks and have each thread have a work queue of smaller tasks it wants to do. So when one thread finishes, you steal work from the other until everything is done. Stealing work has a little bit of overhead because we have to lock, but most threads most tasks are cheap. There's no serialization. We're just passing some pointers in memory around. And that way we ensure that we're using all the threads all the time and everyone finishes at the same time, as long as we can sort of split that task up correctly. And for this example with the single column, you might say, okay, that's just easy, like just chunk it up a little bit. But when you're working on like query plans, you don't always know how the data is going to look like or how your cardinality is going to look like. If you have a group by, well, you haven't seen the data yet, so you don't always know that. So it's a hard problem to split these things up correctly. Yeah, so by now, hopefully, you've sort of looked a little bit beneath the surface of Polars. I mean, you've seen our API, you've seen a bit about the query optimization, and a bit about the query engine. I mean, we could spend hours and hours and hours below the surface talking, but I think for the purposes of this meetup, hopefully it provided a little bit of a nice overview of everything that's happening underneath, and sort of gives you a little bit of reasoning about writing your queries. Of course, I encourage everyone to try it out. I'm not going to do a live demo. I'm not that brave. But yeah, if you have a data wrangling problem, if you're a data engineer, and I encourage you to try it out. It's open source. You can just pip install it, start using it. We'll have user guides and everything to go around. And hopefully it's a nice experience. We have quite an active community. So if you ever bump into something on the Discord or on Stack Overflow, people are usually very happy to help find the answer to the most weirdest queries that get written. We're also, a shameless plug, we're hiring. If you are, or if you know people who love like low-level optimizations or avid Rust users, then please let us know. We might open up some more positions later this year, more towards the Python or DevOps sides, but for now, we're really keen on finding people in the Rust community. That's it. Thank you.
I'm going to share a few slides actually just as a general introduction, and then Vineet will actually take over. We have created a nice demo using Polars with ClickHouse as a real-time data warehouse. And that's basically where I want to start, actually as an introduction. I mean, there's a few show of hands of people actually using ClickHouse already today, but some of you are completely new. So ClickHouse is, as it says, it's a database, data warehouse. It's a columnar-oriented database. So instead of using rows, if you use Postgres, for example, MySQL or Elasticsearch, for example, and you want to do real-time analytics, you need to read the whole row. In ClickHouse, it's all stored in columns. And it only stores data if there's actually a difference, for example, between the point of data before that. It compresses extensively, I would say. To give you an idea, 100 terabyte in Postgres is about 10 terabyte in ClickHouse. So we usually see a factor 10x compression when you move data over from, let's say, MySQL, Postgres, Elasticsearch, to a certain extent MongoDB, InfluxDB, etc., to ClickHouse. Storing data in columns has a lot of benefits. We know exactly where the data is stored. You only need to read those columns where you want to extract the data from, where you want to do the aggregations. So ClickHouse, in that sense, is a real-time data warehouse for real-time aggregations and real-time analytics. As a database, it's important that you've been around for some time. Databases don't pop up from nowhere and then all of a sudden start to become super popular and attractive. So ClickHouse, the first line of code was actually written 16 years ago. I think that's important when you develop a database and when you develop, let's say, features and functionalities. And then, interesting enough, I used to work for Elasticsearch, for example, before, and quite a few people at ClickHouse used to work at Elasticsearch. It's where the code is being written and the company actually is being developed at the same time. And in this case, it's slightly different. The project went open source 7 years ago. It's got about 35,000 stars on GitHub for whatever it's worth, but it has seen quite a nice trajectory in terms of adoption across the world, I have to say. And so, being in existence for 7 years, we created a company 2.5 years ago, in the summer of 21. We're based here in Amsterdam. We've got about 180 people employed, and I guess by the end of next year, we're around double that. So we see a tremendous growth in the adoption of ClickHouse. What is important with an open source project, we're an Apache 2.0 licensed software, you need contributors. And so, for example, if you look at ClickHouse, we've got over 1,500 contributors. If you look at the activity in the community, it's actually quite big. So that's super important for an open source project like ClickHouse. And we actually merge, and that's also interesting. I mean, go out there to GitHub, and with some other databases, there are hardly any external merges, for example. All the merges, everything that is actually being released is coming from the company itself, and I think that actually makes it quite attractive to work with ClickHouse. We're super active in that space. And here you actually see the trajectory of ClickHouse compared to the, let's say, Elasticsearch, MongoDB, etc. So maybe going back to where we are, a real-time data warehouse. And so we're all familiar with the Hadoops and the Teradata and the Oracles of, let's say, 20 years ago. Then 10 years ago, we saw, let's say, the more traditional cloud warehouses, or like Snowflake, Redshift, and BigQuery. And where we're moving to is, let's say, real-time data warehousing as a next generation. We see an enormous growth of data. I think you all experience this. You see this in the observability space. You see this in all your click data, in your sessions, in your events, transactions, everything, all the data is growing extensively. And with let's say the more traditional systems, performance becomes an issue. I think the ones that are here in the audience that is using Postgres or MySQL try to aggregate, let's say, 10 gigabyte of data or 15 gigabyte of data or more, and you see everything become super slow. And I think that's exactly where ClickHouse kicks in. So we see a lot of adoption where people use Postgres or MySQL for their transactions, the record of state, but when they want to do real-time analytics, real-time BI, ClickHouse actually becomes an add-on, let's say, on top of Postgres and MySQL. But we see it in many different other variations as well. And then, of course, there's the cost. So systems become slow, particularly more traditional data warehouses become slower and slower. And if you want to do customer-facing analytics, where you have, let's say, 100 people or 1,000 people querying the data at the same time externally, you need a database like ClickHouse. And to give you an idea, one of our largest users is TikTok. They're running 4,500 nodes, and they serve 70,000 users querying the data at the same time. So particularly customer-facing analytics, where you need the speed, the consistent latency, and the high concurrency, ClickHouse is the choice. So moving from, let's say, traditional data warehouses, and I think you're all familiar with this, where on the left-hand side you see all the data ingestion, all the different sources, moving into lakehouse or any other definition of data storage, data warehouses, into data warehouses on the right-hand side, the visualization, and then, of course, observability at the top, where all the logs, the metrics, and the traces, but also your network data, your Kubernetes east, west, north, south data gets stored, and you want to bring this all together and do analytics on this data. And so here in yellow, you see actually where ClickHouse is actually active. So on the data lake, particularly on the object storage, but then at the top as well, logs, metrics, and traces, and then on the right-hand side, let's say, the more traditional data warehouses. And so to visualize this in a better way, these are actually the 4 sweet spots of ClickHouse. There are many databases out there. You're working with many of them. Some databases are used in the right way, but you also see a lot of use cases that are actually where the database is getting abused, and they're actually not the right fit. And sooner or later, you figure out actually that the database is not the right fit for your use case. So let me focus, let's say, on the 4 use cases to give you some idea that if you want to use ClickHouse, where to focus on. Let me start, let's say, with real-time analytics. So if you're using tick data, so particularly in the finance space, Web3, so all the blockchain data, transactions, clicks, events, sessions, that's why it's called ClickHouse, but also in the network space, etc. All the type of data that you want to ingest in real time, millions of events or clicks or transactions per second, and aggregate them in real time and then use them for all kinds of analytics using standard vanilla plain SQL. That's basically where ClickHouse comes in. So on the left-hand side, you see all the events, all the streaming data coming in, using Kafka or any other form, let's say, of ETL, ELT tool actually to get the data in. Then we have a product called ClickPipes, which is basically a visualization of all the data. You can actually store it immediately in the right columns. And then basically you load the data real-time into ClickHouse. And then you use Grafana, Superset, Tableau, any other way. Basically, you can use APIs, whatever you want to use to visualize and take the data and run that in real time. I've listed here a few examples. I mean, here around the corner, Bitfavo is using it, for example, for tick data, click data. So anything that you see in the Bitfavo app in real-time analytics is basically ClickHouse. You see it with Spotify. If you're a singer-songwriter and you want to understand all your trends, same for Marktplaats, by the way, if you're a professional seller, all that real-time analytics basically is listed there. Then I would say the next use case is real-time BI. Maybe slightly similar, but again, if you have, let's say, all the data on the left-hand side from object storage, for example, ClickHouse can read directly from Mongo, from MySQL, from S3, from GCS, any way to read the data directly into ClickHouse, and then use the different table engines. ClickHouse got about, I think, 7 or 8 different table engines to load the data real-time into ClickHouse, and then basically use the visualization tool. And here I listed, for example, some of the telcos. And we're talking here about companies that actually put 500 terabyte, a couple of gigabyte of data. I think the largest user that we know of is a search engine optimization platform out of Singapore, storing 55 petabyte of data. And that's already compressed. So the equivalent is, let's say, tenfold of that in let's say, an Elastic or any other database. I already mentioned Elastic. I didn't know when I joined ClickHouse. I thought real-time analytics, real-time BI, okay, I get that. But then we actually came across quite a number of companies that said, yeah, well, traces are actually sort of time series, and logs can actually be quite ingested very efficiently into ClickHouse, particularly if as a fact, ClickHouse is built on C++. And as you probably all know, Java is very inefficient with the heap space, the garbage collection. So to run, let's say, efficient terabytes of data in logs per day, ClickHouse is actually a super good alternative. Not only the compression, as I mentioned, to Elasticsearch, for example, but particularly, let's say, in terms of the cost, but also the concurrency. So using Grafana, we actually built our own connector, which is supported by Grafana itself. You can use anything, you can use your logs, your metrics, and your traces, and visualize that, do the alerting through Grafana at, let's say, 10x lower storage and cost. Cloudflare, I would say, is probably one of our largest users, but also DHL, VDL, yeah, maybe not a good example anymore. They stopped producing cars, but they actually moved over 2 years ago. It wasn't the reason, let's say, for them to close the company. So maybe actually one step back, the other traditional use case we see is actually replacing, so for real-time BI, real-time analytics, but also maybe observability, we see a strong migration from, let's say, BigQuery, Redshift, and Snowflake to ClickHouse. And that's mainly driven by cost, because of the storage, but also because of the way we actually propose, let's say, ClickHouse. If you want to run it open source, it's of course at zero cost, in terms at least from a license and from a software perspective. So it's lower cost, factor 10x, 100x, 500x, depending on where you migrate from in terms of query speed, and you have the high concurrency built in, all using standard vanilla plain SQL. We do joins, so it's a really an efficient tool to use. The last one, I would say, is particularly around Gen AI and machine learning. So ClickHouse is often used as a vector database. So if you want to have a fast, efficient database where you can store all these terabytes and petabytes of data for all your modeling as a feature store, for example, that's a typical use case for ClickHouse to store all the data and then run the queries. So we've actually listed here, so these are, for example, A/B testing, all kinds of machine learning where they test the models, store the models, do the calibration of the models. GitLab is exactly, so all the MLOps in GitLab is all run on ClickHouse. So how does this look like? You can start today, tomorrow. It's a single binary. It's a simple curl that you can download from the website. It runs within a couple of minutes. There are different versions. So you have ClickHouse Local that you can run on your laptop. You have ClickHouse Server, and then we offer also ClickHouse in the cloud, and that's basically what you see here. So on the left-hand side, it's a fully distributed setup. Like I said, TikTok is using 4,500 nodes. I would say on average people are running 3 to 4 nodes. They use very large machines, so we see VMs, let's say with 400 terabyte of storage and running, let's say, 1,000 gigabyte of memory. You can fully replicate, do all the backups, you can run it in Kubernetes. All the connectors, all the documentation, everything is there. Go through a course actually how to set ClickHouse up. Use ClickHouse Keeper, for example, for all the sharding and the replication, and off you go. On the right-hand side, you see ClickHouse Cloud. It took us a year actually to build a fully serverless cloud model where we separate the storage from compute. All the data gets stored in object storage, and then with caching and compute, we read the data, process that in real time without any tangible delay, but you do have the cost savings, let's say, of storing your data in object storage. We're working actually on the open source model that you were to run on your own laptop is exactly the same model that we run. The only difference is that we, of course, in the cloud, we're able actually to create all kinds of tooling around it to make it more efficient, more resilient, and more, and I would say even faster in the end than what you were to run in your own machine. I mean, again, if you're using SSD everywhere, you're paying the cost, but then you have the speed. ClickHouse Cloud won't meet, let's say, any of the SSD speeds, of course. I mean, but then with object storage and the auto-scaling, you're able to optimize your costs as well. That's where we are. Any questions so far?